Hello, everyone. Welcome to what will be pre-lecture 16. And this we're going to do another practice problem related to acid base and salts, and then also do an introduction to buffers, although that will be more in class. So something to look forward to. Right, let's see if I can get this to go forward. There we go. Okay, so something that we haven't discussed explicitly, but I thought may be good to bring up just in case you were having trouble understanding what makes a strong acid a strong acid. It relates back to what we talked about at the beginning of the semester, determining bond polarity through electronegativity, and that will lead to essentially a greater dissociation. So the one exception to this is HF. So HF is just kind of a weird exception, but otherwise when we have hydrogen bound to something that has a pretty high electronegativity, we see a greater acid strength. Okay, so again, generally speaking, the more electronegative an atom is, the more polar that bond is, leading to a stronger acid. This is balanced, so the reason HF is an exception is because it is balanced with atomic size. So the smaller our X atom, or the smaller the thing that hydrogen is going to be bound to, the stronger it will have a bond with H+. The stronger bond it will have with H+. And so with HF, because it is the smallest of our halogens, it means that it has actually a pretty strong bond with H+, despite it also being a very electronegative bond. Okay, so that's just why HF is a weak acid as opposed to HCl, HBr, HI being more acidic. Okay. Another trend that we can think about in acid strength is the formation of oxyacids. So I have the chlorine oxyacids shown here as an example where essentially the more oxygens we have, the stronger our acid becomes. And so the Kas are shown here where our Ka for perchloric acid, so HClO4, it's one of our strong acids. And so we say it doesn't have a Ka because it fully dissociates. Chloric acid, HClO3, has a Ka around 1, and then HClO2 has 1.1 times 10 to the -7th, and chlorous acid, 2.9 times 10 to the -8th. So essentially, the less oxygens we have, the more basic it gets, or less acidic it gets, we could also say. And so we're going to do a little further practice with this. So this is a problem that was pretty similar to ones we talked about last class, because I think this is an important concept for you to get. So I will do another practice problem here where we have, or we're asked to calculate the pH of a solution that is 0.25 molar in sodium chloride, or hypochlorite rather. So that's this NaClO. This is essentially what bleach is. So this would be a concentrated solution of bleach. I give you the Ka value. Again, might be important to determine whether it's the Ka or the Kb that's needed of hypochlorous acid HClO, and that has that value. And I ask, will the solution be acidic, basic, or neutral? And so before we start anything, I would recommend starting with this problem. So will the solution be acidic, basic, or neutral? We know that if HClO is a weak acid and we are starting with the sodium salt of it, it means we're starting with the conjugate base of a weak acid. And if we're adding a base, or a conjugate base in this case, to pure water, we know that the final solution should end up basic, right? Be basic, as I tend to say in class. And so by the time we get around to calculating a pH, we should just make sure that that pH is, in fact, something that is above 7, which would indicate that it is basic and follow our thing. Okay. So give me one sec here. Okay, so starting this problem, I would recommend with our equilibrium problems, always write out the equilibrium reaction that's going to be important. And so in class on Tuesday, we talked about splitting it into 2 steps, where if we have a salt, we can think of that dissolving being our first step. And so I'm just going to do this step implicitly in my head, but instead of writing it out this time, since we're getting a little bit more advanced here. So if sodium ClO dissolves in water, it's going to dissociate into sodium plus and ClO minus, right? And those are both going to be soluble. So if I look at these, I know sodium is the conjugate acid of a strong base, sodium hydroxide, so that's not going to affect our pH. And so the thing that we should care about is our ClO minus. And so moving on to what we've called step 2, we have ClO minus. We can write out a reaction with water with that, so with H2O, and that will be a liquid, of course. That will be in equilibrium with our conjugate acid HClO, which will be soluble, and OH minus, which will also be soluble, right? So that is our chemical reaction of interest. We can also write out our K expression here. And so K is going to be equal to HClO times OH minus over ClO minus. That's just our products over our reactants, right? You'll notice that I didn't put Ka or Kb. And so take a moment to think to yourself, do we need the Ka here or do we need Kb? And hopefully you've come to the conclusion that we need to use Kb because ClO minus is going to act as a base when it reacts with water in our chemical equation there. And so we're given the Ka, and so we can find our Kb by rearranging our Kw expression. So that's going to be Kb being equal to Kw over Ka. And so if we plug in those numbers, it'll be 1 times 10 to the minus 14th over our Ka value of 2.9 times 10 to the minus 8th. And I got a value of 3.45 times 10 to the minus 7th for the Kb value, okay? So we'll come back to that in a little bit, but we can build our ice chart now. And so hopefully you're pros at this point where we plug in our initial concentration of the solution here. And sorry, it disappeared there, my E disappeared there. And so if we plug that in, I get 0.250. Water, we don't need to consider because it's a pure liquid, and then our initial concentration of our products will be 0. We have minus X plus X plus X. I can write things here. Then at equilibrium, we'll have our initial concentration minus X, X, and X. Okay. So we've built our ice chart. We know we should be able to now plug our equilibrium column row values into our Kb expression. And so I'm just going to plug in our numbers and our variables. We determined that Kb is 3.45 times 10 to the minus 7th. So that will be equal to x squared over 0.25 minus X. I'm realizing X is 0 there. Sorry about that. You're on the wrong side. But that's why we catch our mistakes, right? And we can always look back to the problem. So if we solve for X here, we can use our X is small approximation because our K value is less than, or we could say more negative than 10 to the negative 4. In this case, it's 10 to the negative 7. And so using that assumption, I got a value of X equal to 2.94 times 10 to the negative 4. And so this is where we need to take a moment, do a conceptual check, since we've solved for X, maybe reevaluate what the question is actually asking us for. And it is asking us for pH. And so with that, if we're trying to solve for pH, we need to figure out what X actually means. And so X, if you look back at your ice chart, hopefully you can see X is equal to our concentration of hydroxide, right? It's also going to be equal to our concentration of HClO, but for our purposes, that's going to be equal to our concentration of hydroxide. So we want to get our pH. We need to figure out how much hydronium we have, so H3O plus. That is going to be equal to, again, our Kw expression, where we have 1.0 times 10 to the minus 14, divided by our concentration of hydroxide, so 2.94 times 10 to the minus 4th. And I got a concentration of hydronium then of 3.40 times 10 to the negative 11th. And so just a reminder of what I did here is that Kw is also equal to our concentration of hydronium, H3O plus, times our concentration of hydroxide. I just rearranged that equation and solved for hydronium plus there. And so that is equal, this value is equal to H3O plus. If we want the pH, we just need to take the negative log of that. So I did that when I took the negative log of 3.4 times 10 to the negative 11th. I got a pH value of 10.47, should be equal to our pH. Okay. With this, we can go back to the original question that we answered. So will the solution be acidic, basic, or neutral? We said it should be basic, and we do indeed have a pH above 7, so it is indeed basic. Okay? Yeah, basic, as I tend to say. Hope that was helpful. Please let me know if you have any questions, and I'll see you in class.